So here we have a bicycle wheel, and if we're willing to assume that the mass of the spokes is really small compared to the mass of the perimeter of the wheel, then, well, the shape is basically a hoop or a ring or a hollow cylinder. And we've already found that the rotational inertia of a hollow cylinder when rotated about an axis passing through its center is equal to just mr squared. Okay. And when we see a wheel move from point A to some point B, so maybe the wheel has rolled somewhere farther down the road to point B, then these two spokes are now somewhere maybe down here, right? And then we're imagining that it is rotated about an axis passing through its center. But I'm not so sure about that. How about this? What if we imagine inserting a meter stick and attaching it across the diameter of the wheel? And instead of allowing the wheel to roll this far, what if we just went back in time a tiny bit to when the wheel was right here, and we move forward a little bit so that the wheel ends up over here? Then the contact point where the wheel is touching the ground has hardly moved at all, and all that's really happened is it looks like this meter stick has swiveled, and a little bit earlier in time that meter stick was leaning back this way, and as the wheel rolls from here to here, the meter stick passes through an upright position and moves to here. In that view of things, it appears that the wheel is rotating about an axis where the wheel meets the ground. So the question is, what's the rotational inertia of a ring or a hoop or a hollow cylinder that's rotated not so much about an axis passing through its center, but an axis that's been shifted to some other distance, but an axis that still lies parallel to the original one? This is a reason for the parallel axis theorem. So we'll say that I center for a hoop is equal to mr squared, but I for, we'll say, about an axis passing through the perimeter of the hoop is equal to not so sure. Well, without deriving it, I'll state the parallel axis theorem. It says I prime, which is like the new rotational inertia after we've shifted the axis, the new rotational inertia after we've shifted the axis should be equal to the original rotational inertia before, when the axis was through its center. That's the key. I naught always represents the rotational inertia for the object with an axis passing through its center. Well, if the distance we shifted the axis is d, and provided that that shift doesn't rotate the axis, it maintains an axis in the same orientation. In other words, the new axis lies parallel to the original axis, and the original axis passed through the center, then I prime and the original aren't equal. The difference is equal to the mass multiplied by the distance of shift squared. The new rotational inertia is equal to the original rotational inertia plus this amount, md squared. That's known as the parallel axis theorem. And so in our example of a wheel, that's 3D, right? I'm not trying to draw a line at a 45-degree angle. This is the x-axis, that's the z-axis. The x and z-axis are in the plane of the page, and then the y-axis is the axis of rotation for the wheel. And then we imagine moving the axis of rotation down to here, so maybe there's y prime, and we've shifted in our example the rotation axis by a distance, well, in general we call it d, but in this case our shift is nothing more than the radius of the wheel. So I naught, the rotational inertia about the original axis, is mr squared. So I prime would equal I naught plus md squared, or in other words, I prime would equal mr squared plus mr squared. We would get I prime equals 2 mr squared. Let's do another example. What if we had a solid disk, like a flywheel, rotating about an axis through its center and parallel to the plane of the disk, and then we choose to shift the axis. We grab our drill and we drill a hole through the flywheel exactly halfway to the edge. So this distance we can say is r over 2. And then we make a new axis and we rotate about something passing through that hole. Notice that the original axis and the new axis lie parallel to each other. So what is the new rotational inertia now that we've made this shift? So the parallel axis theorem tells us that the new rotational inertia is equal to the original rotational inertia plus the mass of the object times the distance by which you've shifted the axis squared. So our new rotational inertia in this case is, okay, so what was the original rotational inertia? I believe when a solid disk has an axis passing through its center, that gives us a rotational inertia of 1/2 mr squared. And then in this case, we've shifted the axis by a distance of r over 2. So we need to take that value of r over 2 and square it. So now we get that the new rotational inertia is 1/2 mr squared plus, let's see, this 2 gets squared, so we get 1/4 mr squared, right? 1/4 mr squared, and 1/2 plus 1/4 gives us 3/4. So there's the final answer in this example. I prime would be equal to 3/4 mr squared. Gosh, let's do another example. What if we had something like a hollow sphere? And very thin-walled hollow sphere. Now, an axis that passes through its center gives us a rotational inertia of 2/3 mr squared. But what if we welded or somehow adhered some small little tube to the edge of it such that we'd be able to pass a rod through there? And so we've shifted the axis, and now we're going to take this whole object and spin it around this new axis. Parallel axis theorem, I prime equals I naught plus md squared. In this case, I prime is equal to 2/3 mr squared plus m. There's another example where d is the full radius, so mr squared. So we get 2/3 plus, I guess that's the same thing as 3/3. So we get I prime is equal to 5/3 mr squared. Plenty of examples of where we might want to apply the parallel axis theorem in future units of study. We'll refer to the parallel axis theorem quite often.